recently, since you've been focusing on the tests, let's go back over to remind us of it.
We're not going over the exam.
Not today. We'll do it on Monday because I didn't have it finished yet. Sorry, I always try to get the exams done as fast as possible because I know everybody's really excited about that. Like, not from a excited in a good way, probably, but nervous about what they got. So, but I will get them posted as soon as I can. Probably won't be till this weekend, but I'll do it as quickly as I can. What? I know. I'm sorry. All right. So we talked about organic chemistry. We talked about these molecules made from carbon and hydrogen and some of their names. And we looked a little bit about isomers, about building some different ways of putting the carbons together that we then fill with hydrogen. And then we ended with a big part of this chapter, which is naming these things. So how do we take a structure like this and give it a unique name that can only apply to that particular structure? And I'm just realizing now this is actually the other class's notes, even though it's the same stuff, but we can, right? So we did a little bit more practice in this last time. So we looked at some of these kinds of simpler structures, butane, and then when we put this extra thing on there, that became 2-methylbutane. So let's review these rules, and then we'll keep practicing the naming and keep looking at some of this naming. So first, we're going to always find the longest chain, the longest continuous line of carbons. Then we're going to find the substituents and number the carbons so that the substituents are closest to 1. So we use the lowest possible numbers. Everybody sort of remember doing this? Maybe a little? Okay. So to practice this, we did a bunch of other different ones. But I want to kind of practice 2 things at once. We talked about isomers as being molecules that had the same formula but were connected in different ways. So hexane is C6H14 and has this kind of a structure. Six carbons in a row with the hydrogens around them also. And so when we name this, we count the longest chain. 1, 2, 3, 4, 5, 6. Doesn't have anything else on it. So 6 carbons in a row, that just makes it hexane. So now we're going to try to find more isomers, that is, other molecules that are also C6H14, but are not connected in that same way. So go back, you can kind of go back to what we were looking at up here. If you remember when we looked at isomers of pentane, we took the carbons and then we disconnected them and stuck them on in different places to try to find some different molecules that have the same formulas. So let's do the same thing now with isomers of hexane. See if you can come up with any of them at all, and we'll see if we can find all of them. See which ones you can come up with, and when you think you've got one, let's put it up on the board like we did last time. So we can see all these isomers. Please, yeah, as soon as you see any, go ahead. Remember, the sooner you go up there, the less likely someone else is taking yours. So. Okay, what do you think about this one? Okay, we'll leave it up there for now. You like it? Okay, good. All right, let's find some more. There are a bunch here. There are, I'm trying to find out exactly how many there are. Yeah, so this one may not have the right number of carbons, right? So that's one thing always to check in your isomers. Every one we draw must be C6H14, so 6 carbons and 14 hydrogens. And how many carbons do we see in this one? Yeah, I see 8, right? So you want to edit that, maybe take 2 of those off and see. See if you can get rid of 2 of those so there's just 6.
Can I show you something before I put it up?
Yeah. Nobody's gonna laugh at you.
Well,
Okay.
is that wrong?
Yeah,
Yes.
but it might be a good thing to see anyway. Yeah. Oh, I'm gonna run out of memory here. Sorry, I can't close my program. It's sort of important right now. All right, so one thing that we should look at, it's actually an issue with both of these, as well as the one that you were too scared to post, is we have to think about the number of bonds to carbon. How many bonds does carbon have to have? 4, always 4. It's got 4 valence electrons, so what's 4 bonds? In organic compounds, always 4 bonds. So if you think about something like this carbon here, how many bonds does this carbon have? Let's count. 1 going from carbon to carbon, right? And then 1 going to one hydrogen and 1 going to another hydrogen. So that's 3 total. So that carbon's not right, it doesn't have enough hydrogens. So these are gonna have that same problem, right? As well as-
Wait, how does that three, when it's carbon to carbon and then hydrogen to hydrogen? It's four.
The CH2 means
Oh, okay.
this.
Okay. Got it.
So perhaps it's helpful to not abbreviate when we're trying to find these isomers, at least for now, so that we can see if there are problems. So here's another problem. This was written as CH2, but that makes that carbon have 6 bonds. So that must not be a CH2, that must be just a carbon with no hydrogens on it. And then this one must need an extra hydrogen over here to give it its 4 bonds. So the solution to this, so this doesn't become a problem, is when you draw these isomers, just leave the hydrogens out. It's not a correct structure to leave the hydrogens out, but it's a starting point. So if we draw the structure like this, just the skeleton of carbons, then we can add whatever hydrogens we need to make sure that we have enough bonds to carbons, and then we can count them out. So this one, anything on the end must need 3 hydrogens. Right? Close that off. And then over here, and here, and there. So now every carbon has 4 bonds. We can count up the hydrogens, make sure we have 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're okay. Now maybe if we wanted to make it look pretty, we could condense these back and do a condensed formula and make these into CH3 and this one into CH2.
Do you have to?
No, I mean,
Okay.
depending on what you need. The idea is to have facility to go back and forth as needed. So we can actually fix this one. We need to get rid of 2 of the carbons, so we can get those to make it 6. And then if we fix the hydrogens here, we realize that the outside ones all need to be CH3 because we need to have 3 hydrogens each. And then these need to have 1 so that they have 4 total. Now that's a good structure. And then our next question is this different from this one? But we'll get into that in a bit because we can use those names to help. So let's try to find a few more and then we'll start looking at the names. See how else you can do this. Nobody found any more?
I thought we were waiting for you. What are we waiting for?
Oh, I'm waiting for you.
Oh, that's what he's saying.
Yeah, so we got to find some more C6H14s other than that one and these 2. There should be a couple more.
Besides the long chain.
Yep. So we got the long chain. We got these 2.
Mm-hmm.
What else can we find?
Can it be? No, it's not.
Right, we can't have any rings, any closed like rings or
Cyclo.
cyclo anything, because that would lead to a lower number of hydrogens. It wouldn't be the same formula, those would not be isomers.
I don't like this.
Well, then, let's see
Show
what
you
they work.
one.
Okay, so
Probably
you
wrong. You can say no, it's wrong.
I'll look at it so we can learn
about why it
might not be
Just look at it first.
It's the ones.
Okay,
That's no. Probably no way.
it's. It's a correct structure, there's nothing like wrong with it like there were with these other ones at first.
The first.
Shut up.
I would
Okay,
think
no.
What's going on?
Another one I have. How does it kill you?
No fights here. No fights, please.
I had a similar structure to that one, except
Yeah.
I did, instead of there being a C in the middle, I put like C to C, and then arrow down from the last C to C to C, and then kind of like a stair step,
Put it on the board. So we can all see.
probably not.
It's a good description, but let's see.
Right here. There's too many.
What's too many?
There's too many hydrogens.
There's one HM between two C's, which is not on your right.
I think
Which
that's
one?
meant to be connected just to this carbon here.
But he's counting it at each.
Yeah, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14.
You sure?
Yeah.
I'm gonna put a red dot. Yeah,
And 6 cards, right?
yeah.
Yeah, so that's good. Okay, so we got a few up here now. Got 4 of them. So now the question is, well, I'll tell you, they're all correct structures. They're all fine. We've gone through and fixed those couple. They all fit the 6C6H14, and they all fit the rules of 4 bonds for carbon and 1 bond for hydrogen. As far as I know. Does anybody see any errors in those? I think they all fit. So the next question is, are these the same or are they different from each other? They look different, but they may not actually be different molecules, because remember that single bonds can rotate, we can flip these things around, and just looking at them, it's really hard to figure out whether they're the same or not. But there's an easy way to do it. Well, I'm not going to say an easy way, but there's a good way to do it, and that is to name it. We go through those naming rules. Anything that's the same is going to have the same name, even if it's drawn all weird. If it has the same name, then we know it's actually the same, and those aren't separate isomers. So let's go through and follow our naming rules and try to figure out what these names should be. All right, so this first one, over on the, we'll start with the far left. Looks like this. Make sure I'm transcribing it properly here. And I'll just add in the hydrogens like this, just to make it a little quicker. Is that correct? Is that the same as that? Would you say?
No.
It's not? What's different?
No, that's right.
It is? Okay. Okay, so let's look at the naming rules. What's the first thing we do in our naming rules? Find the longest chain. So what's the longest continuous chain here? Which way? I'm just looking for color. So we use red for the longest continuous chain. So the carbons connected to each other, how many do you get? Which 5? This one? 1, 2, 3, 4, 5. Why can't we add this in here? That's connected, right? As long as we're still being connected, we can go any direction, any way we want. So 1, 2, 3, 4, 5, 6. So really this is the longest chain. And are there any substituents? So what do we call this?
I thought the thing we just threw in there is the substituent.
This?
Yeah.
It's not, because it's really part of the longest chain, because it's still connected to all these other carbons. Right, if it were coming off here, then we'd have to pick our pen to go to the next, to cover everything. This way we can keep going, okay, this one's next to this one, is next to this one, next to this one, next to this one, next to this one. That's the longest connected chain. Longest chain where everything's connected to each other. So what does that tell us about what this is? Is this an isomer of hexane? Not exactly, because it's the same. So these two are the same. Even though they look different, they only differ in the orientation or the bend of the bonds. Since they have the same name, they must actually be the same molecule. So this would not be an example of an isomer of hexane. This is just hexane drawn another way.
What's the same?
This molecule is the same as this molecule. It's just drawn differently. Right. Okay, so now let's look at the next one. Next one looks like this. So what's the longest continuous chain we can count on this one? Straight down, right? Or this one, or this one. Either way, they're all 4. So sure, we'll just take this one. So that's 4 carbons, and that makes these other 2 substituents, right? So how are we going to number this chain so that the substituents get the lowest possible numbers? We're going to number from top to bottom or from bottom to top? Top to bottom. Yeah, because that way it's 1, 2, 3, 4, and the substituents are on number 2. If we started at the bottom, they would be on number 3. So we want the lower number. All right. Okay, so then what is our name for the longest chain? Butane. And what are the substituents? Right. So these are methyl substituents because they're just one carbon substituents, but there's 2 of them. So that makes it dimethyl, and they're on carbon number 2. So that makes it 2, 2 dimethylbutane. So clearly a different name from hexane. But it still is C6H14. So that means that this is an isomer. Yeah. If you go back to that practice test from last year, one of the things you'll see, and a nice way to ask about these kinds of things in a multiple choice exam, is I can say, okay, which of the choices is an isomer of this structure? And so you have to go through all of them, make sure that you're looking for something with the right formula and that is connected in a different way. All right, so it would have a different name. We'll go through some practice like that. Let's continue then. The next one over is this one.
Oh my God.
Let's see if you can name this one on your own. Same rules as the previous one. See what you come up with.
Still like the same thing, but it says like not 2, 2, like 2 dimethyl
So what is it?
as an isomer.
It is. So what would the name be?
2 dimethyl butane, but not 2, 2 dimethyl.
Why just 2?
Because
So here's your longest chain, right?
like when it's second and third.
Right. So here's your longest chain, and there's the 2 substituents, which means it doesn't matter which way we number this. So there's a substituent on number 2 and a substituent on number 3, a methyl on 2 and a methyl on 3. See that? So that makes this 2, 3. Dimethylbutane. All right, so that was 2, 2. This is 2, 3. And so again, this is different. So these are separate molecules, different compounds. Okay, let's look at this final one. Same thing. See if you can find the name. Right. What'd you say? Say it again. What was your name? 3-methylpentane. Yeah, I think that's right. Let's look at it. So our longest chain is this. Right? 5 carbons in a row. 1, 2, 3, 4, 5. Can't get any longer than that. Which makes this a substituent on the 3rd carbon. 1, 2, 5. So that is 3 methylpentane. Okay. So we almost got them all, actually. There are 5 isomers of hexane. Here are 4 of them. There is one more. So let's do the one more, the opposite. I will write the name of it, and you can write the structure from the name. Okay? So the last one is, the one that we didn't get, is 2-methylpentane. Let's see if you can draw a structure for 2-methylpentane. And if you think you've got it, let's come put it up on the board with all the other ones. Anybody feel good about it yet?
Wouldn't it just be the last one that we did, except the substituent will be the carbon above it as well?
Yeah, you also have to change, so same thing we did here. That's connected right in terms of carbons, the hydrogen are not in the right place. But yeah, you're also thinking the right way. So if the last one we did was 3-methylpentane, then we can just move that methyl to carbon number 2. But we have to change the hydrogens, or we're going to have too many on one carbon and not enough on the other.
So there's 5 carbons, right?
5 carbons and then a 6th one coming off of number 2.
All right. Like a T? Skeletal?
Yeah. Anybody want to try to put it up there? Yeah, go for it.
Well, I'm gonna go first.
Okay. Yeah, except for the hydrogens.
Otherwise, this one's like what I said.
So this carbon is one more than that. Try drawing them out
Okay.
instead of abbreviating them
Now I
so you can
it.
see.
But I get
Yeah.
it.
So there should be 12 hydrogens.
14. Still 14.
Doesn't pentane 5 and then you double 5 and add 2? And do 12?
Oh, but we have a sixth carbon coming. I mean, the total structure is
Oh,
going to have 14.
Yeah, this should be right, huh?
What?
This one has one.
Yeah, I think you're right. Go ahead and put it up on the board.
I did uppercase T, now lowercase t. Yeah.
Yeah, so let's put that one up. That looks good. Thank you. All right, so that is 2-methylpentane. Now, remember, we also note here that it doesn't matter, the angles of the bonds here or the orientation this thing is written in doesn't matter, which is why we have to stick to this name. So if you wrote something like this, whoops, that's also 2-methylpentane.
But if you compare it to this one, it's not an isomer, right?
It's not, so these are the same. And if you flip that over or turn it around, or maybe you like the more correct bond angles, we talked about how it's not actually straight in a line, it's more like this. Right, still the same. Those are all 2-methylpentane. And I think the thing that most people get tripped up on with finding these isomers is mistaking this for different when they're actually the same. Is that thinking that just because this one looks a lot different from this one, those must be isomers. They're not, they're the same. And the name is really the key to that. If you can easily, or not, maybe not easily, what? What?
You count the carbons and the hydrogens?
Yeah, but all isomers are going to have the same numbers of carbons and hydrogens.
So then you would need to see the.
You would,
substitution.
yeah, or which is another way of saying look at the name. If the names are the same, then these things are the same. If they're different, then they're different, then they're isomers. That's really the lesson here. Okay. Ready to move on from this? Okay, the next part is to look at a different way of drawing the structure that is a lot easier, excuse me, easier and quicker to draw than this, but it makes a few more assumptions that we have to be aware of. These are called line structures, or sometimes skeletal structures. We'll stick with these hexane isomers because that's what we've been talking about. Let's put hexane down here. This is what we call the condensed structure. Another way to draw this, and a more common way, is like this. That's the line structure. So what does that mean? Well, a couple of rules about line structures. In a line structure, I guess I'll tell you about it and then we'll write it down in the official rules. In a line structure, rather than showing the carbons and hydrogens, we simply show where they are. We realize that we don't actually need to show the hydrogens because we always know how many are supposed to be there because we know carbon always needs 4 bonds. So this is a way of abbreviating that and saying, well, we're only going to look at the carbons. And the way we look at the carbons is by using these angles. So we assume a carbon anywhere that there is an end of a line or 2 lines or more lines coming together. So in this structure, if those are our 6 carbons, 1, 2, 3, 4, 5, 6, those are our 6 carbons in our line structure. You start to see that so far? So let's look at some of these other isomers that we've dealt with. This one we just did, the 2-methylpentane. Now we're going to draw a chain of 5 carbons with 1 coming off the second one. So that's going to look like this. 1, 2, 3, 4, 5.
Wait, can you do that again?
1, 2, 3, 4, 5. Let's number. Just like this. 1, 2, 3, 4,
From 2,
5.
you're gonna draw like another.
Right. So from 2, we got to draw another one for that extra carbon here.
What do you label that? 6?
Yeah, I mean, I guess that's the 6th one, or whatever you want to call it. So that's our line structure or a skeletal structure for this 2-methylpentane. So drawing the line structures from condensed structures is a lot like naming. We want to find the longest chain first, and then draw that in our zigzags, and then stick everything else coming off of it that we can. So give that a try. See if you can draw these other 3. Oh, wait, we already did this one. So these other 3 in line structures. Or pick one and try it. And if you think you have something that might work, come put it up on the board so we can see how it fits.
Wait, for which one?
Any of the ones we haven't done yet, so the 3 on the right. Yeah. Pick one of those and try it.
ones are not condensed structures, so it's a little bit.
Right, so you may want to redraw them as just the carbons or something first. You want me to go up to the other one?
Would they come out like that?
Kind of. I mean, it's that idea, but they'll look a little bit
I
different.
think I got it.
You got one?
Yeah.
All right, put it up next to whatever its structure is.
Okay.
Thanks.
Is that right?
What do you think?
No,
How confident are you about it?
not confident.
Not confident?
No.
Okay. Anybody else? You think that looks good? You think that looks maybe?
Oh, okay.
You did the one that she did?
Yeah, but it's okay, let me try the other.
Okay, so see what you come up with. Nobody has anything to say about that structure? Good or bad?
Which way the line goes, like,
No.
like, I mean, like on the third one,
Mhm.
coming up top, or just put it on the bottom, doesn't matter.
Right. Good. That's a good point. Let me draw that. Go ahead. Go ahead. Whatever you do. So the question I think is,
This way?
would it matter if you did it like that?
It doesn't look right, it looks kind of strange, but yeah.
Right. So that's the thing. Technically, yeah, this is a correct structure. This is also correct, by the way. Should be
It's
confident.
right?
Yeah.
What about this? This is a little bit different. You know,
Holy
so
shit.
that's not same.
Yeah, it's also right. But this would also technically be correct, but it kind of looks funky. So we usually try to put the substituents out so that these angles stay big. If you see something with the like skinny little angles, that's probably not as nice.
That's why I did, because I thought the 2 going down, if I were to put the 3 going down, it would look too crowded.
Yeah, right, exactly. So when it looks too crowded, best put it somewhere else. Put it
So if
on the
you
other
put
way.
it up and then the other one down, would it be wrong? Or both down?
I mean, this is how this should be drawn. This is how this should be drawn.
No, I'm asking if I put it down too, would it be wrong? Like
No, I wouldn't mark it wrong, but you wouldn't see it like that in a, you know,
On a test.
It wouldn't
or a
look-
final.
right. It wouldn't look, well, remember their final is multiple choice, so
All of it?
you're not gonna draw it anyway. But like on the quiz next week, yeah. On the quiz next week, if you were to draw that down, that would be okay. Yep, that looks good too. So that's another way to draw this, right?
No, I'm trying to.
Does it have-
Like one.
Okay, but then you've got the muscle groups on. Yes. That's right.
I did it last year.
But you can't move it to a different curve,
Yes.
so you have to just kind of.
Her process, 1 hour.
Okay.
What happened?
All right, so we've got another line structure here
Dramatic.
for this one.
That is offensive. in a way.
Can it?
What?
Have you seen Nicki Minaj's new album cover?
No,
She's getting a lot of heat for it.
there's all the chemical structures on it.
Yeah, exactly.
Okay. All right, so the only one we don't have a structure for yet is this one over here. You refused to that one?
Or it has to be?
I bet you.
No, it can be any way at all. Now, and that's actually a good point. So when we draw the line structures, it's less likely for them to get as messed up as some of these, just because of how we think about them. So if you always think about making your longest chain in a line structure, just go straight across, and then you can make things come off, you know, wherever you like. So what's the longest chain in this one? 5. Right, 1, 2, 3, 4, 5. So if you make a zigzag of 5, and then you can make that methyl group come off the right spot. See if you can give it a try.
What was it condensed one for the one that I gave? Condensed.
What?
How is it condensed?
That is condensed for the one you did.
That is?
Yeah.
Okay.
That's what you did.
Multiple choice, everything for the final exams.
Everything? Oh, thank you.
So all the answers are right there for you. I'm not sure thank you is the right response.
Wait, what?
At the wall, it's multiple choice.
The other exams, usually the multiple choice is a little lower than the rest of the exam.
You get more points when you do the written part.
Right.
Mhm.
I don't like multiple choice.
No, I know they me confused. Sometimes we have to do the same.
Yeah, and I don't know many my meeting.
And they, well, that's not a great idea. But the final will also be, even though it's a final, a little bit shorter because the final exam period is a little shorter than the regular lab period.
What's the time?
I don't remember, we have to look at the
Hour and a half.
schedule. I think it's a little more than that. I think it's an hour 45 or 2 hours, which most people have been finishing the exam in that time, but it needs to be shorter to accommodate that. So, I don't remember. I'll have to look at it again. All right, so we got one more structure. Anybody?
It's
Anybody
just
got
like
it
an
yet?
M?
Kind of, but you got to remember to get that extra substituent in there.
Yeah. Off of the 3. Right? You do it off of the 3. The substitution on the 3. Point or the 4?
It's on the 3.
Oh, okay.
Looking good so far? Maybe? Go ahead and leave it on the board. I can see it. Looks good. This thing up here.
And that first one all the way on the left,
Mhm.
the line's going down, like it's going on the other side. Like, the air, but it's fine, right? It looks strange, but good.
Yeah. So you far left over here. Yeah, I mean, a slightly clearer way to write this would be like that. Just because it's more standard to do that. Okay, so we've got some structures and their accompanying line structures. And there's a bunch of examples of this in the book, so you can go back and look at that. But the big advantage of this, even though it's a little tricky sometimes to actually do the conversion from one way or the other, is that it's so much faster to draw these things this way. So let's work on some other ones now. We'll try a couple for practice, and then we'll take a little break and come back and move on to something else. So now, since we know how to do this, I'm going to draw some line structures and ask you to name them instead of condensed structures. You may find that they might be a little easier or maybe harder. I don't know. I think a little of both, maybe. Yeah. Yeah, I want you to name these. And then I'm also going to draw, going to write a name and ask you to draw a line structure for that name. This is going to be all right, so names for the two structures on the left and then a structure for the name on the right.
So for the first one on the left, the M shape before the other ones that carry down.
Yeah.
Would those be the substituents? That are down?
Not
or
necessarily.
would it be seven?
Not necessarily.
Does it go up to 8?
You
Is
have to
there
find the
an
longest
option?
chain first, and then you can look for substituents.
For the one that's on the end, would there be 2 carbons?
Right.
Those ones?
You're trying to name the 2 on the left, or the left one and the middle one, and then a structure for the one on the right,
Oh,
and then draw a structure for the one on the right.
Excuse me?
Yeah.
What did you say we're doing with this one?
You have to do the same.
Give the name for this, and then draw a structure for this name.
Oh, the name for this and the structure for this one.
Oh, we're just naming, and then drawing out.
Yeah. Naming, and then drawing a structure.
Mhm.
Right.
What?
you want to see it?
No, just tell me. What do you think? You got one for the first one? What'd you come up with?
3 for hexing.
That's what you got too? Okay. Anybody get something else? Yes, no, maybe? A little? Same. Okay, great. So you found that the longest chain was this here, which is 6 carbons. 1, 2, 3, 4, 5, 6. And a substituent of 2 carbons, which is an ethyl substituent coming off of the 3rd carbon. 3-ethyl hexane. Great. Nice job. Okay, what about the next one?
3, 6,
Hexane or heptane?
Hep- hep-
But you went with hex?
And when we have X, yes, this is like.
Okay.
Oh, yeah, it is.
Yeah, so. What about the rest of it?
The numbering is my issue, because I don't know where to start, and I know
Which
that
one is one and one?
Right, because when they're in a circle or in a ring, how do you know where to start? Because you can start anywhere, there's no end.
Right.
So how do you start? What do you think?
That's my question. If you start from where the
Mhm, you got it.
yeah, if you start numbering from that one,
Mhm.
it sounds odd. Like say one, and then the other one will end up with 5. Will be good. Let's say,
So you're going like this way?
yeah,
What if you go this way?
yeah, that's anti-clockwise.
Either way.
Okay.
So the answer to the question is, you start wherever you can to make the lowest numbers, just like in a chain. In the chain, you start from whichever end gives you the lowest numbers for the substituents. In a ring, you start anywhere that gives you the lowest numbers. So for this structure, the lowest numbers are going to be 1, 2, 3, like this. Or because it's symmetrical, 1, 2, 3, 4, 5, 6. Either way.
So 1 and 3, right?
Right. So either way you do it, the numbers should come up with 1, 3, which are lower numbers than 3, 6. And that's the correct name. Right. Yeah. So you got the structure for the last one? Want to come try to put it up here and then take a little break?
Anywhere.
Yeah.
Something like that.
Something like that. What do you think? Thanks.
I feel like little mouse and thing. Is that wrong?
The little mountain thing. So yours look more like.
Like I did it like, what you put?
Wouldn't it be, instead of it going right there, wouldn't it be the last one on the bottom?
So
One from the top, the other from the bottom, because it's 1, 3 diethyl.
You talking about?
I think that was.
Oh,
No, I'm talking about what you just said.
it's 2.
Why?
It's 1, 2, die. Like the.
1, 3 diethyl.
That's a 3 or a 2.
Good.
Which one do you guys talking about?
The one that
The
you
middle
did,
or
the
the
one that, oh, like that.
There, yeah.
1, 2.
Oh, I did that one. The one you wrote out that we have to draw.
Yeah, it's 2.
Yeah,
Shouldn't it be
that looks good to
3?
me.
Why would it be 3?
What?
I didn't start on that one, I drew the last one.
Which one? Oh, it's 1 dash. Oh, I know it's 1.
Yeah, so that structure looks good to me. A cyclobutane is a square or a diamond shape, however you like it. And so then you're going to have 2 methyl groups kind of coming off carbons next to each other. All right, let's take a little break and then we'll come back and move on.
sucks.
Snooki's new husband pleads guilty to DUI.
Who? Snooki?
Her husband.
She done, he gonna divorce her once, he gonna get all her money.
No, he signed a prenup.
He didn't.
He didn't sign a prenup?
She didn't make a plan.
Am I the one who thinks that she looks better
Yeah,
when she was like a little bit thicker and looking so weirdly skinny?
Yeah, she looks like a chipmunk now.
She looks a lot of.
I don't, you know what, it's not the fact that she's like super like 90 pounds and a bag of bones.
I can still
Because of
across
her
the room.
veneers.
Huh?
The veneers she put on. If she had put on, including Dina, the other one, she looks like whack job. She looks like she has dentures in her mouth.
Oh,
Like she's an 80-year-old mouth.
So, I really wish they would show us now. That was a professional in the world.
Me too.
Amazing.
Maybe we were offensive when I said the public side.
oh, I
I
didn't
thought the
make
same
that.
thing. I'm sorry.
He
Yeah,
probably
that's exactly-
did.
Yeah.
He's definitely. Definitely.
I mean-
He looks it,
Like, whatever.
just like the way that she's young. I don't know.
I think it's
It is?
pretty, I mean, I'm sure, but.
He looks it.
Maybe if I make him mouth false, they'll give me a secret.
Yeah.
So serious. God, I was at a moss ball kick like for 2 weeks, a couple months
Pretty
ago.
good.
Oh my God. I was screaming it so bad. My boyfriend's like, pregnant with a Jew or something. I think it's bullshit that he's not getting us a study packet for the final.
I thought he said we're gonna do like a review.
In class.
In class.
Oh,
Yeah, we're not gonna get a packet, but
He never
Basically,
gave us study guides. It's not that surprising.
yeah, it'd be cool. Like for real.
If I-
Yeah, that's
it is a final.
Wait,
And-
you're surprised by it?
Right.
No, I'm not surprised. It's just,
You just like, come on.
give us some
Exactly.
fucking rope to hang ourselves with.
No, he said review the old exam, so that must mean he's gonna put full questions from all those exams, and that's what he better do. There's nothing new gonna be on there, but I need a review of chapters 6,
Yes.
the dumb stuff, like that, when all the math just got crazy,
Sure.
molar and all
Oh,
that dumb
okay.
stuff.
Ugh.
That's what I need to review.
Oh, you mean like converting moles to
Mhm.
rounds and?
Yeah.
I'm constantly bitching to tell my parents the final isn't until after Christmas.
They
Because
won't
I'm
believe you.
surprised. No, my parents have moved to Florida. I'm surprising them on Christmas.
Oh.
And my dad's like, don't even think about coming down here. School's not gonna play.
Well, yeah, just tell them whatever. Yeah, and then you get surprised. So yeah, like,
Yeah.
I have a final, sorry, it's like the 30th or 25th, whatever. Or yeah, 24th, Christmas 25th, right?
They really want.
24th, 23rd.
But they
It's
like-
a surprise.
Yeah, so like the 28th or something. No.
Or if they ask, I'll just be like, he hasn't posted the grades yet, Dad.
Or say you have to register for classes, so if you don't before a certain time or something, and say that you need to be here.
Yeah.
Um,
Oh, no, I already have a
That
flight
puts you
home.
here.
Oh, I already have a flight home.
No, but just say something that puts you, that you have to be here.
Like the school,
Work.
old school, I actually come in and fill out a paper for the classes that I want to join.
Right.
I have to get back home because of my thick boss.
Perfect.
What part of Florida?
Boynton Beach. My puppy lost his first puppy tooth today.
15th. Oh,
Thank God.
Yeah.
Yeah, they're fucking daggers.
God.
They're so
I
sharp.
wouldn't know what to do if I saw a dog and teeth just laying around.
I can't wait to see him toothless.
It'll probably grow back. I mean,
They grow back into the adult teeth that aren't as sharp.
I didn't realize that any of our dogs wash their teeth until I stepped on them and go, oh, shit, it's the teeth on the foot.
Yeah,
So the teeth that falls out is
it's
bigger
just like
than
a
the-
human.
Yeah.
It's just like a human.
Yeah.
Your children's teeth are sharper than the teeth you have now. He's teething, like, he sticks my whole hand in his mouth. He doesn't chew on it, but I can feel on the bridge of his gums, like the adult teeth coming in, and it's like a happy dance because this asshole has ruined
chewing things up.
my car seat, my leather seat. When he was like, when I brought him home 2 weeks after I brought him home,
How many teeth are gonna fall out? All of them, or just like-
majority of them, yeah. They'll grow in a lot faster than humans, so he's not gonna look like a mouth.
That would be cute.
I wish. How cats get declawed. Puppies would get like deep. He's such a chunk.
That's what we did in my first day.
Oh, no.
Totally tore it
I
up,
would
and
never
that's
get back
just,
in my car.
that's how big he was when he did it.
He'd be kicked out of our car. So yeah, you said you work at the vaccine grocery. I need to
I work at the retail hospital, like, they post jobs, like, if you wanna work, so like, I work across the street, right, or like, they'll post jobs that are only available to associates who already work there. That's what they do most of the time, but like, give me your number, and then, because we get like weekly things, it's like this position's open. You know.
Because I filled out for a position, it was in the behavioral health building.
Okay.
I don't care, I'll do it.
I mean, whatever,
But
I think it's kind of fun.
Right, so it's like, it's never the one in behavioral health, it's like always. But it's like, I'm getting feedback yet.
Like, there was one girl, she broke her foot or something. She's a little older, and like, she broke her foot at work, and now there's a bunch of randoms kind of working, but we're all short now, so we're gonna hire someone, I'm assuming.
And what position was she?
She's just a PCT. I mean, there are no LPNs there.
No.
It's just either you're a PCT, if you work at like, there's a place where you can be a PCT too, across the street, or you're just an RN.
So why do they have a position open for? Because I think a lot of places do that, they'll say they're looking for LPN, and then you go there, like, no, you don't have to hire.
Yeah, because like, there's already, but there's a girl there, she's an LPN, she has her stuff, but like, she's only PCT, because there's no job for it, it's just either you're this or you're that.
Is she still in school?
No, I mean, she's like 50 or something. Yeah, but I mean, like, whatever, like, they pay for your school and stuff, so whatever.
But she's not in school.
No, she's such a
Like,
PCT
if
job.
that happens, like, they put her as a nurse. And she was just a PCT, and they'll take her license. That's why I stopped working immediately after I had school. You just snatch your license.
What?
People who like work as CNAs or PCTs while they're licensed or have passed their boards or something. So
Oh,
they'll-
nurses who work as CNAs?
Right.
Why would a nurse want to fucking do that?
Like, over at Alexi Brothers, at least where I work, there's no LPNs, it's either you're a PCT or you're an RN.
Yeah.
So there's a girl there who's an LPN, she has her stuff, but she can only get PCT unless she wanted to finish school, which she did, so she was with PCT. So if something happened to someone, I mean, even though it would be on the nurses, it would be the nurse
It'd be
that
the
would
nurse.
deal with it, but like,
But when they do like an investigation, they'll see everybody and they'll look her up and they'll see that she was a nurse, they treat her as a nurse.
yeah. Well, like where I work, I don't know if they would do that. They're free, like, I mean, like, they would throw them on nurses, but they would, yeah, like.
No, but Candice, it's like this class is only example, when I sit in this class and I was not thinking of Candice every time. I should try next time with them.
That's true. He might have some.
At least we have one more class.
Before, I'm just.
You should have brought like, there's a whole bag of like Holland candy in there.
Bring it next week. It's gonna like make the class go fast and.
We're just doing the lab. How about this? I volunteer to check everyone's lab drawer if the guy gives me extra credit.
What? We talked about that last time. You said no.
No, I said I would clean the whole lab.
You know what
Not-
you need to do? We just need to negotiate.
I think so.
All of us.
Yeah, all of us. How
But
many-
I think I need it more than anyone in this effing class right
That's
now.
what you think.
That
That is true, because I do this in my.
Bullshit, my overall grade right now is 65. I'm not passing.
I don't think you're at work.
65. Swear to God.
Just talk to him. Talking to him by yourself, he's not going to do it. Not gonna do it.
What are you gonna
As
say?
a class is
No.
No, we just, I need to talk to him, all of us, like, we all need to do good, so.
How do you feel about this next exam?
No.
I mean, the exam you just took.
I
I'm
think it's
not
gonna work because.
confident.
In my side, how is it, class?
About where?
Because like. what?
I'd be lucky if I got a 50.
That's not
How about, I just need a 70. Can I just ask him, can you please give me a 70 for my overall grade?
You could ask them, I'm probably gonna say no, but you can still ask.
You guys, you just need to negotiate with him.
I don't care if it's a 70.1.
Like, say one
Like I
thing.
said, yeah, like it's all of us are.
We need to talk to him like as a class right now, and then see what we can do. Maybe he can give us a better. Huh?
Are you guys testing?
Very, nothing, very. Yeah,
Sorry, are you getting a 65?
Who?
You.
No, I'm somebody.
Okay.
Oh my God, 72. 2.96, so.
Shut
I don't know if he
Then where are
rounded.
you?
I
80?
was surprised by that. I'm not gonna tell you guys now. I was
You
surprised.
already
Oh,
told me, you
sorry.
were at a 78 before.
Oh, yeah, I did tell you
So
that.
you probably at an 80, because he added all that.
Right there.
He was at 80, so he has nothing more.
Did you add something to it? I didn't see him.
Yeah, I
add
think
anything
he
to mine.
I
think he did take out something because when I checked, I got.
And we had like.
I don't know how it comes about,
because I think it was something outside.
He took some of the things out. No, you guys, when you talk to him, he's
Yeah,
supposed to
he
get
did
your.
yours. But he said the
He already-
application
I
has.
thought he already did that. like-
No, he said he had.
That's what he said.
Well, we haven't completed all the tests. For someone who's getting an 82 in class, you're pretty freaking stupid.
Well, I thought he said.
What?
Wait,
That's what
we've
he
only
said.
taken 3 tests now.
Yeah.
Can we bribe him? With what?
There's only
Well,
like
we
6
did-
of us.
Wait, he said he's married, right?
Yeah.
What if I tell him I will give your wife free Botox and Juvederm at my office if you give me a 70?
Yeah.
They wouldn't buy into it.
No, just that.
Because that's bribery, and that's like a felony or something.
Listen, you guys.
He loses his job.
Exactly. You want, listen, the best thing that we can do is something fair. Let's just all talk to him in class. Then if he wants, he's gonna give us maybe another quiz or
No,
something.
you know what we should
I
make
think
sense?
that's what
Is
he tried
that
to do with
if
the extra
this
points.
last
That's
exam,
the
if you got below a 70% on this last exam, that he can override letting us correct our mistakes and then getting half credit for it, so at least it's not a failing grade necessarily.
Don't give them your suggestion. Just ask him, and then he's gonna say what he wants. Don't, if you tell him like, let's do this, he wants to do it. He's like, you're telling me what to do. No, let's just tell him, I think we're not doing very good and we're a small class, don't do it, maybe you should.
And let's say
try
for.
to-
You want to say no.
We're talking about it anyway.
Sure. All nice things, I'm sure.
Can I go? Can I ask?
question. I'm
So I'm
delegating.
just wondering that we don't think we will be doing very good in this class.
Okay.
And what do you think that we're going to do?
Not just like extra quizzes, but like so that they can
Please, we are too
substantially like do something. Because I know I'm speaking for myself, my grade, I probably should have dropped, but I had hopes of something, whether I did relatively okay on this, better than what I have been getting in my prior tests.
I don't
Well, that's
think it
good.
was good for us to be 6.
Well, I mean, hopefully this exam will be good when I finish grading it. But really, the biggest thing is the final, is a lot. Because it's 15% on its own, and then it can also replace your lowest exam, which is another 10%. So you're talking about a quarter of your grade potentially still to come.
And the percentage that we see on Blackboard, that doesn't include our our worst exam.
Does it include it or not?
It does not include. So what you see on Blackboard is dropped. The lowest exam is dropped.
No.
So you're right.
Told you, son.
Okay. I was saying.
Sorry for calling you stupid.
Right, so it will always, now that we'll have a third exam, when that gets posted, the percent on Blackboard will take the highest 2 exams.
So is that the right grade?
Yeah.
So you're saying when you grade this one, you're gonna drop again? No.
No, when this one posts, the final grade will take into account top 2 exams, rather than just the top 1. And then when we have the final, it will take the top 3, including the final, and then the other final. And then the final will count on its own as well.
Is there anything else we can do?
No. So we will drop, we'll drop 4 quizzes. Because we have had 8 and we'll have the 9th next week.
What are we?
And so we drop 4 quizzes and count 5.
And labs, you drop labs.
And drop 2 labs and 2 pre-labs.
And we're still gonna get points for that lab too, right?
Yeah. Yeah, keep reminding me. Gotta get points for that too.
So I think it might work out. You just gotta put.
Well, it's not just gonna magically work out, but if you do well on the final, then you should do okay. But the reason there's not extra things, I don't think we didn't go through, talk about this in this class, but your final grade needs to be a measure of your mastery of this material, how well you understand and can perform these types of things that we've been talking about. So what, I'm not sure, I'll have to check and see. But so if I don't have a problem saying things like, if you do well on the final, that will count a lot and can change your grade, because if you do well on the final, that means that you've mastered the material, at the end, a decent amount. But what I'm not willing to do is to say, well, okay, all your exam scores show that you're at a D, so just do some extra stuff and then magically you're at a C. That doesn't make sense. That's not you doing some, it's like saying, well, I've done a bunch of bad work all semester. I just want to do some more bad work and then get a good grade when you take all the bad work into account together. And that doesn't make sense. Your grade needs to be a measure of how well you can show that you've mastered the material from the class.
When you say do well on final, what exactly is well?
It depends on how the rest of the semester has been going
Exactly well.
and how. If you want to come see me sometime, we can play with some of the numbers and you can get a sense of that. But,
Can we play the memory?
well, you can play with them whenever you want. The percentages are all in the syllabus, so you can just look it up and do it. But yeah, the final is worth 25% of your grade. But also, the final is a pretty good measure of everything from the whole semester. So, if you've not been doing well on all the exams, something substantial has to change if you expect the final score to be any different. That's just kind of compounds.
I don't know. Lord have mercy.
All right, let's move on. Okay, so everybody's good with naming and drawing?
Good?
Maybe good is a little strong for now, but you got to start anyway. You know, do a couple hundred of these in your homework and you'll feel a little better.
So that's called drawing. That's just drawing.
Yeah, drawing structures, naming compounds.
Line structures.
One thing we didn't quite mention is that we should. Here. Halogen substituents. So all the structures we've looked at so far are alkanes, meaning they're just carbon and hydrogen single bonds. Of course, there's lots of other types of compounds, and we're going to go through some of them called alkenes and alkynes, but we're probably not going to get to all these different ones. But one very easy one is if you have a structure that has one of the halogen elements coming off of the carbon chain. Something like this. That Br would be bromine. Right? We can name the halogen substituents just like we name everything else. Oops, let me put them in order here. These are very common ways to make these compounds more reactive, to make them do things. And so these different substituents are called fluoro, chloro, bromo, and iodo. So the naming rules still apply, nothing changes, except we use these substituent names instead of things like methyl and ethyl. So how would you name this molecule then? This one. Yep. 3-bromobutane? Everybody agree? Not quite. You're close, really close. No. So you say 3-bromobutane. It's almost right.
Is it 3-bromo tributane?
No. It's the number actually that's wrong. 3 is not correct. Why is 3 not correct? Right, because it should be 2. Because we have to number the chain so that the substituents get the lowest numbers, which means we need to start numbering from the right in this case. So that should be 2-bromobutane, not 3-bromobutane. So that's, other than that, that's pretty much it. Okay. Other words that are used to describe these compounds are saturated or unsaturated. Have you heard of saturated fats or unsaturated fats? What do you think that means? It's actually a chemical description.
It's made up of, it's a chain of carbons with a lot of like hydrogens,
Mm-hmm.
like in carbohydrate, sugar.
Sugars are actually a little bit different, but you're right. With fats, it has to do with the hydrogens. So yeah, yep. We're going to be that's right for the fats. We're going to be a little more general than that. But these terms saturated, what does that term mean, like in a non-chemical sense? If something is saturated with something, it's full of something, right? Like if your coat is saturated with water, because it was raining. It means it's totally full of water and it doesn't get any more water. We also talked about saturated solutions versus unsaturated solutions a few chapters ago. So kind of full of stuff. So saturated in the organic chemistry sense means full of hydrogen. As much hydrogen as there can be for the number of carbons. And we know from the stuff that we've done so far, if you have, let's say, 4 carbons, what is the most hydrogens you can put in that molecule? 10. Right, you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So the most saturated carbons would be the first one.
No, actually, we're talking about the molecule as a whole. So we would say the molecule is saturated. So this is butane, and this is a saturated molecule. Because you can't have any more hydrogens in that molecule, or you'd violate the bonding rules and it wouldn't form. So then how would you have a compound that has less or fewer than the maximum number of hydrogens? Yeah, some of the carbons won't have as much hydrogen, but they still need 4 bonds. So what can we do instead? Yeah, we can double bond carbons. So something like, let's look at a structure like this. If we have those 2 carbons on the left sharing 2 pairs of electrons instead of just 1, now there's not as much room for hydrogen anymore. So we'd still have 3 over here and 2 here. How many hydrogens would be on this carbon? Just 1, because it's already got 1, 2, 3, so that hydrogen is a 4th bond, because that double bond counts as 2. So then over here, we would have just 2. Carbons all still have 4 bonds, but this was C4H10, and this one is C4H8. So this would be unsaturated. And it could even be more unsaturated, right? We could put more double bonds in there. We could put a triple bond. So we could have something like this.
What would be the name for that?
Well, I don't know if we're going to get to
Then never mind.
that, but
So.
we'll get to the alkene. We'll get to the double bonds, but not the triple bonds. But the answer is, it's actually pretty simple. Instead of ending the name with ane, you end it with ene for a double bond. So for this one, then, we lose 2 more hydrogen
There's a triple bond.
because of that triple bond. Because the carbons still need 4 bonds
That's
each.
Unsaturated bond.
So that's still, yeah, also
It's a
unsaturated.
big indicator of it being unsaturated, the double bond, triple
Right.
bond. Okay.
Right. So if we go back to fats, saturated fats are fats like, fatty acids, like stearic acid, which are these long chains of carbon, 16 or 20 carbons in a row, all with hydrogen, single bonds with hydrogens on them. And those are known as saturated fats. Unsaturated fats, things like olive oil, oleic acid, have double bonds in the chains. And so they don't have as much hydrogen in them. And so that's where those words come from, and this is sort of the chemistry behind it. There's one other way to make an unsaturated compound without using double or triple bonds. You know what it is? You can connect things in a ring. So if we think about cyclobutane,
That's saturated.
it's not, because it doesn't have as many hydrogens as this. So per the 4 carbons, this one is,
The same thing as the.
yeah, this one is C4H8, so that is still unsaturated. So the main things you want to look for unsaturated are rings and double or triple bonds. If you have those in there, then you know it's unsaturated. So you can see as you start getting more unsaturated, the number of potential isomers goes up. Like we had 5 isomers of, well, if we have butane, there's only 2 isomers of butane. There's the straight one, and then there's the one that kind of looks like a inside of a Mercedes, you know, that car side. That. So that's, anyway, so there's only 2 of them. But if we took 2 of those hydrogens away, now we can have double bonds, we can have rings, we could put that double bond in another spot, we could rearrange the carbons and have a double bond. So there become a lot more options, a lot more possibilities for isomers. We won't get into a lot of that here. But that's saturated versus unsaturated. So let's look at drawing a structure, because this idea can help you to figure out how to draw a potential structure. So let's say I ask you, draw a structure with formula C5H10. Well, that's the first question we've got to ask. So if it's saturated, this question's really easy because it just means we could just draw this 5 in a row and then do it. Is that going to be a saturated formula or not? How do we know?
The 5 is all the C's are going to have at least 2 hydrogens.
Right. But how many do we want total for a saturated? Anybody remember that number?
C with 3 and then 2.
Close.
C's.
So in a saturated compound, however many carbons you have, let's just say N, some number of carbons, you'll always have double the number of hydrogens plus 2 more for the N's. So if you have 5 carbons,
Yeah, 12 hydrogens.
you need 12 hydrogens to be saturated. So if you only have 10 hydrogens, that tells you it's unsaturated. So that means that the structure that you draw should have what?
The 2 carbons, like one hydrogen.
Yeah, that should have some kind of way to have fewer hydrogens. It should have a double bond or it should be a ring. So when we're drawing this, then we might draw it like this.
Couldn't you just do C with the 3 lines?
The triple bond,
Yeah.
that would actually take away too many hydrogens because the triple bond, every double or triple takes away 2. So a double takes away 2, and then if you went to the triple, that would be 2 more. So that would be C5H8.
So it would just be a double.
Right. And we can count it out to check. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that works. Another way that you could do this would be to connect these in a ring. That also allows you to get an unsaturated structure. All right. So while we're talking about these unsaturated things, let's talk specifically about alkenes. Alkenes, notice the E, that's the important part. Alkanes were all the things we were just talking about, these sorts of things, all single bonds. Alkenes refer to double bonds. And it doesn't seem like that big of a difference. Your carbons are connected by single bonds, your carbons are connected by double bonds, you lose a couple of hydrogens. Shouldn't make that big of a difference. But in fact, it makes an enormous difference chemically. Remember, these alkanes are virtually inert chemically. They can be burned and that's about it. They don't do other kinds of reactions so much. The double bonds do. They do all kinds of stuff. They can react with water, they can react with hydrogen, they can react with halogens, they can react with other carbons. So having a double bond there completely changes the chemical functionality of these compounds and allows you to do more stuff with them. You can use them to start building up larger molecules and to start making things, to start synthesizing drugs or whatever you want to make out of your compounds. Plastics, polymers, most of our clothes, you know, there are synthetic fibers and these sorts of surfaces are all made from double bonds, from compounds with double bonds. And so we're gonna, pretty much the rest of what we're talking about this semester is going to be the chemistry of these things, what we can do with them and what they do. So first we'll look a little bit at the structure. The important thing about a double bond is that it does not twist or rotate the way the single bonds do. So let's take a simple alkene like this, 2-butene, and we'll talk a little bit about the naming. There's actually two ways that you can write this compound, and it's a little different from what we've talked about so far. So look at these two compounds. They both show a line of 4 carbons with a double bond between the second and third carbon, right? The only difference is that on the left, the carbon, the CH3s are sort of on opposite sides, and then on the right, they're more on the same side. Now, back when we were talking about these, we would say, well, those are the same. It's just a twist, and twist is a twist, and it doesn't make any difference. If that double bond weren't there, those two would be the same. But with the double bond there, it's not the same anymore because you can't twist a double bond. So there's no way to turn one of these, to twist it over to become the other one, like there would be with these. But so these kind of need a special designation because they're not exactly connected differently. I mean, the carbons are still all connected in a chain. Double bonds still in the same place. So they're not traditional isomers. So they have a different name, which is called stereoisomers. And you don't need to know that name in particular, but you do need to know how we distinguish these. This one we call trans, and this one we call cis. Trans means opposite, cis means the same. And the way we determine that is we think of kind of an imaginary line that runs through that double bond like this. And then we think, are the things that are the same, are they on the same side or are they on opposite sides of that imaginary
Trans is
line?
opposite.
So trans is opposite, cis is the same. Yeah. So this actually gets added to the name of these compounds. Let me just give you the name and then we'll talk about how we got to it. So this molecule is going to be called trans 2-butene, and this one's going to be called cis 2-butene. So now you know where the trans and the cis come from. The butene is like butane, but since we change it to an E, that tells us there's a double bond. So then what does this 2 mean? Why isn't it just trans-butene and cis-butene? Good guess. Not quite. There's two little things on the end.
There's 2 carbons in the center.
I'll give you a hint. There is another butene. So we need those, well, I haven't drawn it yet. I mean, there exists another one. And so we need that 2 to distinguish from another butene. So let me draw the other one and then see if that makes any more sense. So the other butene is this. And this is 1-butene. So what do you think is the difference between 1-butene and 2-butene? Yeah, where the double bond is. So if we think about numbering the chain, right, we always number the carbon chain just like in the other ones. 1, 2, 3, 4 versus 1, 2, 3, 4. Look where the double bond is. In 1-butene, the double bond is between 1 and 2. In 2-butene, the double bond is between 2 and 3. And those are isomers because the hydrogens are in different places. Those are connected in different ways. So for a double bond, we need to specify where on the chain that double bond is. Is it at the beginning? Is it starting at the 2nd carbon? Is it starting at the 3rd carbon? Is it starting at the 4th carbon? And so on. These cis-trans words are also important when we're talking about fats. So all naturally occurring unsaturated fats are cis, are this way. And what that does is because they can't rotate, if you imagine a really long chain that suddenly gets one of these types of bonds, let's draw that. What that does is puts like a kink in the chain, makes it go around, stops it from staying out straight because it's kind of moved over. So if you compare that to a long straight chain, which is going to look like this, those kinked chains, whoops, I'm forgetting you can't really see that over there. Those kinked chains can't pack as tightly, can't pack with each other as closely. They don't have as strong of intermolecular forces. And so what that means for us is that saturated fats tend to be solids at room temperature, things like butter, animal fat, shortening, that kind of thing. And coconut oil, palm oil. And unsaturated fats tend to be liquid at room temperature, like olive oil, canola oil, because they can't pack as tightly and become those solids. That also happens in our body. So the saturated fats accumulate and pack, especially around our organs, in ways that isn't good for us and form problems in our blood vessels and all that kind of stuff. And the unsaturated fats tend not to do that. Additionally, the reactivity of that double bond allows unsaturated fats to be used for things that are important, particularly in making something called prostaglandins, which are an important molecule in the body. So that's why we need certain types of unsaturated fats. That's why you always hear about omega-3 or omega-5 fats that we need to get. That's a function of how far the double bond is from the end of the chain. So an omega-3 is 3 carbons away from the end. And so those are used in important biological functions. You may have also heard of trans fats. What do you know about those? Chips and stuff. It's a bad thing. Yeah. What happens is you can take an unsaturated fat and you can do a chemical procedure to it called partial hydrogenation. And what you do to that is you kind of stretch it out, but you leave the double bond in it. So you allow it to go from a cis double bond that makes this kink to a trans double bond that allows it to spread out. And that has a couple effects. For one, now it acts like a saturated fat because it's structurally similar. So it can pack really tightly and it can be a solid at room temperature. And the main reason that trans fats were developed was actually just because of marketing. So people started to try to avoid saturated fats in the I want to say 70s. I don't remember exactly. But at some point, the last 30, 40 years, people started avoiding saturated fats. They started to know they caused heart disease and all this stuff. And so they said, okay, no saturated fat. So if companies made their foods with the trans fats instead, they could say no saturated fat because trans fats are technically unsaturated. Though now we know that they're actually worse than saturated fats because not only do they go to the same places that saturated fats do, but they cause damage. They cause more damage in those places than the saturated fats do also. So that's why there's been a big move away from them now. The only real resistance to that is they also have a much higher shelf life than other types of fats. They don't go rancid. So any kinds of foods that have really good shelf life, like Twinkies or things in vending machines, chips, things that need to stay non-spoiled for like years, those tend to be high in trans fats because those fats don't go bad. And a lot of, so if you look at labels, I don't know if anybody has any snacks, like packaged snacks right now, but if you look at labels, if you ever see, even if it says on the label 0 grams of trans fat, if the ingredients say anything about partially hydrogenated something or other, partially hydrogenated soybean oil, partially hydrogenated palm oil is another one, that's trans fat. So there may still be a small amount in there, depending on the food. McDonald's famously finally moved away from trans fats a few years ago. Or if you, where else is it big on trans fats? Oh, popcorn. Has anybody ever worked in a movie theater or seen the fat that's used to pop popcorn? It's kind of looks like jelly and it's pink. It's like bright pink.
It's disgusting.
Yeah, it's pretty gross. I don't know if they still use that. They probably don't, but it's really gross looking. Yeah, it's really gross. But there's so much trans fat in there. But that's why it's so good. But actually, if you want to make really amazing popcorn at home, it takes just like the movie theater, use coconut oil.
Yeah.
That's amazing. That's not really good for you either, but it's delicious.
Coconut oil is very good for you.
It's saturated fat. I mean, it's,
So good for your hair and skin.
yeah, not as good for your arteries,
Right.
but
No, I don't think it's fine.
as long as your hair looks nice. No, right,
Yeah.
right, yeah. Yeah, keep it as a,
But as a hair mask, you're not gonna gain 5 pounds.
right.
in a day.
Yeah, keep it on the outside of your body.
That's
but it is
why it's
delicious.
So good for you.
All right, so that's double bonds, trans cis. We're going to look at some reactions of them too. But let's go back to our naming and see how that might work with some of these extra little tricks thrown in. I don't want to say tricks, some extra little things thrown in. All right, I'm going to draw a couple molecules, see if you can name them. So similar to the ones we've had before, but now with these double bonds in there. Let's see if you can come up with a name.
For the first one, is for
Yeah.
naming it,
do you
do you
think?
go from right to left, and numbering it?
What do you think?
Yeah.
Why?
Because before we started talking about alkaline,
Mm-hmm.
the double bond, you said to keep the numbering and the naming for the substituents or something, to keep it close in proximity in your numbering.
Right, so you want the lowest numbers on the substituents, and in this case on the alkene as well. So
Okay.
which
So
side of the
left to right.
chain? Yeah, so you go left to right, so everything has the smallest numbers.
Okay.
I was still, I'm looking at the bond and I'm so confused whether it is going to be like a trans or a cis because it is not,
Right, so in this case, would it be a trans or a cis?
but I feel like this could be a trans because the branch of.
So let's think about, let's look at what's here. So you've got CH3 there and CH3 here. And so we're looking at a line, an imaginary line through the double bond, parallel with the double bond. And so is this, and then this is clearly the bigger thing on this side, but this one is the same, right? CH3 versus CH3. So there is no trans or cis, because if it were flipped, it would still be the same thing. I know, but I'm saying if we replace this with this, if we replace these two with each other, there's no difference. Whereas up here, right. No, it means that it is neither. It doesn't get that designation because there's no difference. In this case, when you if you were to replace this with this, you would be switching a CH3 and an H, so there would be a difference on both sides.
CH2, CH3 is
So CH3 is the same as CH3. If you switch those, there's no difference. So this one doesn't get a trans or a cis designation. Well, there's nothing to compare it to. It's cis or trans is a relationship between the sides of the double bond. So if one side's the same, then there's no trans or cis. Same thing with this one butene. If we draw this out more explicitly, let's look at this one here. That would be another way to draw that structure. Same as here. So you can see here on this side, on this carbon, you have a big group and a little group. But on this carbon, you have the same thing on both sides. So there can't be any trans or cis because no matter how you draw it, you always have the same thing. Same issue here. Yeah, it's just normalized stuff. So what did you come up with the rest of the name? Okay, 2-pentene. Just like that? There you go. So this would be 2-methyl-2-pentene. The first 2 refers to where the methyl substituent is. The second 2 refers to where the double bond starts. And it's pentene because it's got 5 carbons in the chain. 1, 2, 3, 4, 5. And then we put that E in there. Right? All right, so now that said, see if you can do the next one.
the 220?
Because the double bond starts at the second carbon of the chain. So if we number these as 1, 2,
So where the second bond is for the stop sign is 2, isn't it?
well, again, we're in a ring now, so we can start numbering kind of wherever we want. So you
Would
can
this
pick.
have like a cyclo vaccine?
Mhm.
So if you to cyclohexane,
So again,
to if you to cyclohexane,
so you're saying
my numbers have come down.
1, 2? Okay. Why start 1 here?
Because it's gonna be upward, if you have to start from the one up, then this one down will be 6. So now the one will be between 6 and 1.
Okay, but what about this?
Yeah, that's what I have.
If that is the case, the one is still between 1 and 2.
That's a little better, right? Because now you can have 1 ethyl, 1 cyclohexene.
Okay, 1 ethyl, 1 cyclohexane. So why do we use 1? The bonding is.
This one tells us where the ethyl is. It's on carbon number 1. This one tells us the double bond starts at 1. Goes from 1 to 2. Yeah. Just like this one was 2 to 3, so it was a 2. This one's 1 to 2, so it's a 1. All right, for the last bit, what we're going to do, I want you each to draw a structure, a line structure, anything you want with either a double bond or halogens, anything that we've sort of talked about. Draw a structure, at least, let's say at least 7 carbons. And then we're going to try to name them all. So each person's going to draw 1 structure, whatever you want, anything, is at least 7 carbons. Can have double bond, can have halogens, bromine, chlorine, whatever. Just draw a structure, something we haven't seen yet.
Okay. I'm ready for this.
It doesn't, it's totally open-ended. Just draw the structure, however you want. Yeah, just draw something, and then let's put it up on the board and we'll try to name them all.
Do you have to know how to name it?
You don't have to know how to name it yourself. You just draw, and then we'll work on it together.
Okay.
Right here. Because I can't resolve it. I have a question.
Yes.
If your double bond comes before your constituent, do you name the double bond first? or-
Yes. Oh, no, the double bond takes the priority in terms of the numbers, but you still put the number last, right before the big part of the name. You can try to name your structure if you want, but mostly we just want to get them up so everybody we can all look at them and try.
Work. Just do something once.
Yeah. There's one up in that thing. Yeah. Oh, I meant this, but yeah, that's fine too.
Is that even possible?
Sure.
Okay.
I'm concerned about the number of hydrogens in these carbons. Why don't we?
Oh, I had a job.
I'm trying to figure out.
No, you don't have to. Just stick with the line structure. You don't have to mess with that.
That's it? So I just,
Yeah. Mhm. Yeah. All right, we got 4, so that means we need 2 more. And let's write all these down. Oh, I didn't see the green one. Sorry. Go ahead. I'll copy these down here. So we've got something like that. Okay. Getting tricky here. Okay. I think we got them. All right, these are all reasonable, fine structures. They might look a little wonky, but they're fine. So let's try to find their names. See what you can do. See if you can get a name for each of these. Maybe work together if you feel like it. What? Oh, you wanted me to try to name it? You didn't think I could do it?
No, like, we can do it, but because like, for us, we do what we cannot do.
Oh, okay. Well, yeah, if you can come up with one, that'd be good too. Maybe these will be on the quiz next week.
What?
That'd be good. You guys can write the quiz. You should write the quiz questions for once, so I don't have to work so
Yeah.
hard at it, right?
let's do it.
Where's the double bond on the first one?
The first one? Oh, there is no double bond. It's just that there should be a CL here. I missed that. That's that green one on the far left there.
I have a question.
Yes.
So like, how do you know it's like CL or like VR?
What do you
Is
mean?
it just like written that way, or is it like?
Yeah, whatever the structure is. Yeah. So they're going to have different names.
I don't think so. It depends because like this one, the other one.
What?
You have to figure out the hydrogen, how many, I mean.
No, you don't need to know the hydrogens to get
I
the
mean, the
names.
carbon,
You need to know how many carbons, right, in the longest chain.
but like for the first one,
Mm-hmm.
oh, okay.
So you got to find the longest continuous chain in the first one, and then number it. got any names yet? Got some? Fairly confident about them? A little bit? Who's got a name for the first one here? Give it a try.
So, we went down to ethyl, 3, 4, and
Ethyl or methyl? 2-ethyl, 3. Okay. We get something else?
I got hexene. Is that what you meant?
I said pain.
You did ene?
Yeah.
Okay. So everything else the same? Okay.
I got this instead of 2, ethyl, I got 2 ethyl. That was like 3. Then, recycle is we need
Like that? Oops. Like that?
yes.
Okay. Any others? You got the second one?
Process.
All right.
3, 4, 3, comma 4.
Oh, you got another one. Oops. What did I do?
Oh, for the second.
Oh, you got for this one? What'd you get for this one? 3, 4.
Methyl.
Methyl?
And
Okay. Can we get something different? Let's go back to this first one, because actually none of these are right. That's okay. It's a good start. So we find the longest chain. Looks like you got that one. That's going to be here. Everybody found that longest chain? Or the one that goes up here. Either way. So that's going to be 1, 2, 3, 4, 5, 6. And then our substituent is right here, which is a 1-carbon substituent. So the first name here is the closest. But let's fix it. It should be, I guess it doesn't work that way. That should be 2-methyl, because it's 1 carbon, not ethyl, which would be 2 carbons. And actually, the totally correct name here, which I don't care so much about, but the totally correct name, because we didn't talk about this, but I'll just tell you anyway, is to switch the chloro and the methyl because C comes before M, and substituents are listed in alphabetical order, but don't worry about that. So we'll say this is correct, this one is okay, and these are not correct.
the same as his.
Okay. I thought I said
That's the
ethyl.
thing I'm having trouble with, putting the substituents on the right carbon.
Yeah, so this one's coming off of number 2, and this one's coming off of number 3.
And the chloro,
Mm-hmm.
I thought, cause it had the halogen,
Mm-hmm.
so that would make it, hexene.
Nope, that's only for the double bonds.
Okay.
And then this one is close, but because there are 2 methyls, we have to say, right, 3,4-dimethylhexane. 3,4-methylhexane makes it sound like there's 1 methyl that's attached at 2 different places. So we have to make it clear that there are actually 2 of them. Okay. Anybody get this one yet?
Which one?
What do you think? All right, so that's 2 like that. Yep, that's correct. You may not see where that one comes from. So you've got your longest chain here, or starting from the top, 1, 2, 3, 4, 5, 6. So your methyl substituent is on number 2, and your double bond hexene starts on number 3. Okay, next one. No clue, no idea, nothing. Well, I'm going to edit this one a little bit from how it's drawn up here. Again, it's okay, but it looks a little nicer if we get rid of that weird angle and we put this up here. So we'll do that. Okay. I think that's right. Let's try that. So 5 bromo, 7 chloro, 2 nonene. Because there's 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, yes, you're right. Nonene, 2 nonene. Great, yeah. So you see, even large molecules, you just follow the rules and still works the same way. Okay, we got 2 more, 10 minutes. I think we can do it. Well, let's get this one out of the way. What's the name of that one? This one down here? Yeah. Wouldn't it be nice if I just put stuff like that on exams?
Yeah.
Is there a double bond in that?
There
Or
is.
is that just like, because like
I think it's a double bond, yeah. Yeah. Let's see what you can do with this, then we'll talk about it.
Would we consider like a cyclo?
Yep. Right.
Will we number it for the top right corner and go 1?
Why? What's the rule on numbering?
No, it's, you have to be closer to the double bond.
Right. So we want a
So the
number.
bottom,
We want a number probably right at
the bottom.
here, because then the double bond and this thing get 1s.
Okay.
That's where we want to start our 1.
And then the 2 through 6 or 7 won't really matter.
Right. Yeah.
When you counting the
Mhm.
lines, like this substituent, how do you start from the end point where it touches the line? Or,
Yeah, we have to figure out how many carbons are in here. So you're talking about for this thing here, right? So here's our substituent. And remember there's going to be, now I'm not sure what you meant when you were making it, but from what it looks like to me, we've got to assume there's a carbon anytime there's a bend or an end.
Yeah.
So 1, 2, 3 is what I see, yeah? Okay. And then we're going to count our main stuff starting here. 1, 2, 3, 4, 5, 6, 7. So what did you come up with? Like that? Close. Yeah, this should be 1 cycloheptene because the double bond also starts at 1. 2 cycloheptene would be if we put it over here. And actually then we'd number it completely differently because the double bond gets priority over the substituent. So that's good enough for us for now. 1 propyl, 1 cycloheptene. These are good. These are tough ones. So nice job. You're getting good at this. Keep practicing this. So we'll finish up this chapter on Monday. We'll talk about some of the reactions of this compounds. Won't take a whole lot of time. It'll be after our cleanup from lab, and we'll go through the exam, and then we'll finish up, and then quiz on Wednesday on this whole chapter.
quiz on Wednesday on this chapter?
Right.
Then on Monday, just to bring them up and then we clean them up.
Yeah, and then we're going to talk more a little. We're going to finish the chapter on Monday.